Good afternoon. Today I'm gonna go over some problems that appear already in the previous Putnam competition, and I will try to show you how to solve them. The subjects of today will be the limit problems. So I'm gonna go over a lot of problems that concern limit in this lecture. The first problem that I wanted to show is this problem A3, which was in the 81th computation in 2021. So the problem is as follows. Suppose that A0 is pi over 2, and you define an to be sinus of an minus 1 for n to be bigger than equal to 1. And you have to determine whether the sum when n is going from 1 to infinity of an squared converge. Right. So this is the first problem that concerns series and then limits. And the purpose of our training today is to go over all of those, a couple of those problems. So now I'm gonna give you some intuition on this problem solution. So we're gonna notice that we're gonna first we notice that we have sinus of x is smaller than x for all x bigger than 0. So this is the first thing that we see. So if x is bigger than 0, then sinus of x is smaller than x, and since an is sinus of a n minus 1, all right. So then we're gonna see that this is decreasing. Okay, so this is smaller than an minus 1, meaning that this is hence the series is decreasing and positive. As a1 is sinus of a0, and this is sinus of pi over 2, and this is 1. All right. So the first observation that we have is that sinus is smaller than x, meaning that sinus of an minus 1 is smaller than an minus 1. And because a1 is sinus of pi over 2, so this is 1. And so this is decreasing and positive. All right. Now, this is the first observation that we have, right? So why do we observe? Why do we consider this property? Because an is defined to be sinus of an minus 1. So this makes sense for us to compare sinus of an minus 1 and an minus 1. This is the first observation. The second observation that we have is the following. Second observation. So now for x to be in 0 and 1. All right, we have what? We have sinus of x is bigger than x minus x cubed over 6. And this is basically the Taylor expansion, right? So this is basically the Taylor expansion, Taylor series. So we know that sinus of x is bigger than x minus x cubed. And this is something that we're gonna use because we know that an is sinus of an minus 1. So based on these two observations, we're gonna have the following claim. we have that an is bigger than 1 over square root of n. For n bigger than or equal to 1, right? So how do we prove this claim? So to prove this claim, the only tool that we have is induction, right? So we will prove this claim by induction. So first, for n to be 1, we know that a1 is 1 already. So this is bigger than or equal to 1 square root of 1. This is the first thing. Now the second thing will be the following. So we're gonna suppose that, because this is a proof by induction, we're gonna suppose that so suppose that the claim is true for n to be k. We will prove that this is true for n to be so we will prove that the claim will be true for n to be k plus 1. All right, so first we're going to prove that this is true for k, and then we suppose that this is true for k, and then we're going to prove that this is true for n to be k plus 1. Right, so so we have that. Okay, suppose that ak is bigger than or equal to square root of 1 for k, and we will prove that this is supposed. We will prove that ak plus 1 is bigger than or equal to square root of k plus 1. Right? But what is ak plus 1? Ak plus 1 is sinus of ak. All right? But we know that ak is bigger than 1 over square root of k. Then we have sinus of ak is bigger than sinus of 1 over square root of k. Now we're going to use the observation, the second observation of both, right? We know that sinus of x is bigger than x minus x cubed over 6. All right. So in this case, x will be 1 over square root of k. Then I have sinus of 1 over k is bigger than 1 over square root of k minus 1 over square root of k to power 3 over 6. And we will prove that this is indeed, we will prove right. So this is the second observation. So we will prove that 1 over square root of k minus 1 over square root of k power 3 over 6 is bigger than 1 over square root of k plus 1. Right? So this is something that we have to prove. Now, so if we develop the left-hand side, we're going to have 1 over square root of k minus 1 over square root of k to power 3 over 6 will be 1 over square root of k 1 minus 1 over 6k. All right. And this will be 1 over square root of k 6k minus 1 over 6k. Now we want to prove we want to prove that 1 over square root of k, 6k minus 1 over 6k is bigger than 1 over square root of k plus 1. Now I'm gonna, so which is equivalent to the fact that 1 over k times 6k minus 1 square over 6k square, and which is bigger than k plus 1. Right? So which means that this is equivalent to k plus 1. 6k minus 1 square is bigger than 36k cubed. Now you're going to have to develop this. So you're going to have k plus 1, 36k square minus 12k plus 1. This is bigger than 36k cubed. This is then equivalent with 36k cubed plus 36k square minus 12k square minus 12k plus k plus 1 is bigger than 36k cubed. All right. So we simplify everything, and this is equivalent to 24k square minus 11k plus 1 is bigger than or equal to 0. We now develop the last quantity, which is 3k minus 1. 8k minus 1 is bigger than or equal to 0. But this last inequality is true because k is bigger than or equal to 1. So in the induction proof is complete. And so first we suppose by induction that a k is bigger than 1 over square root 1, which is true. We suppose that the claim is true for n is equal to k, and we want to prove that the claim is also equal for true is also true for k plus 1. So we prove it. Finally, by induction, the claim is true. All right. So because by induction the claim is true, therefore we can claim that we prove that we have proved that an is bigger than 1 over square root of n for n bigger than or equal to 0. All right. So now the sum of n square will be bigger than the sum of 1 square of n, but unfortunately this is divergent. So this is diverges. Finally, the sum of n square diverges. All right. So I explain again. So in this first example, I consider problem A3 in the 81 competition. So in this problem, you consider A0 to be pi over 2 and you define n to be sinus of n minus 1, right? So you have to determine whether the sum when n is going from 1 to infinity of n squared diverges or converges. So the key of this is the geometric series. So you look into an, which is sinus of n minus 1. You want to prove a lower bound for an, right? So the key will be this lower bound. In this proof, the key will be lower bound n is bigger than 1 over square root of n. And because of this lower bound, the sum of n square is bigger than the sum of 1 over n, and this diverges because you know that the sum of 1 over n diverges, right? So this is the first key in proving a series converges or diverges. You want to prove a series that the series diverges, you have to establish a low bound, and the low bound that you can take advantage here is the sinus function. And from the sinus function, you can prove that an is bigger than 1 over square root of n, right? All right, so the second problem that I want to consider is problem number 2, B2. So in the AP, so problem B2. So this is the ID Putnam competition. On 2019. So for n greater than 0, let an should be the sum when k going from 1 to n minus 1 of sinus of 2k minus 1 pi over 2n. All right, dividing by cosinus square of k minus 1 pi over 2n and cosinus square of k pi over 2n. We have to determine the limit when n tends to infinity of an over n cubed. So this is a very nice problem, and the solution is as follows. All right. All right, so solution. All right, so first we observe that. Okay, so first we observe that the 2 cosinus square of k minus 1 pi over 2n minus 2 cosinus square k pi over 2n is, so this guy is going to be cosinus of k minus 1 pi over n plus 1 minus cosinus of k pi. So this is basically the half angle formula. The first thing that I observe is 2 cosinus square of k minus 1 pi over 2n is basically cosinus of 2n minus pi to the cosinus of k minus 1 pi over 2n plus 1, right? So then this is simply a half angle formula. Now in this formula, we observe that we can basically remove the plus 1. So, okay, so then you have cosinus of k minus 1 pi over n minus cosinus of k and k pi over n, all right? So this will be 2 sinus of 2k minus 1 pi over 2n and sinus of pi over 2n, all right? So I explain again. Here I have 2 cosinus square minus 2 cosinus square. So 2 cosinus square is cosinus 2 plus 1. So I remove the 1, and then I have cosinus k minus 1 pi over n minus cosinus k pi over n. So this can be written as 2 times sinus of 2k minus 1 pi over 2n and sinus of pi over 2n. All right. So now we then so this means that the an will be 1 over sinus of pi over 2n of 1 over cosinus square k pi over 2n minus 1 over cosinus square of k minus 1 pi over 2n. All right, so this is an. All right, so now, so because you can write an under this form, the sum is telescope. Thus, the sum is telescope. Okay, so this is the sum. Okay, it's 1 to n minus 1. It's telescope. And we find obtain an is 1 over sinus of pi over 2n minus 1 plus over 1 over cosinus square n minus 1 pi over 2n. All right, and then this is equal to minus 1 over n sinus of pi over 2n plus 1 over sinus cube pi over 2n. All right, so this is basically the sum. So I explain again. First, you observe this identity. Then you write n as this sum. All right. So now you know that this sum is telescope, and you can simplify this sum as follow. Now you're gonna have to take the limit of this one. Right. So the goal here is to take the limit when n tends to infinity of n cube an over n cube. Right. So then there's one identity that you need to keep in mind. Since the limit when x tends to 0 of sinus of x over x is equal to 1, all right, we deduce that the limit when n tends to infinity of n sinus of pi over 2n is definitely pi over 2. All right, so therefore the limit when n tends to infinity of an over n cube is 8 over pi cube. All right. All right, so let me explain again. So the key of this problem is you have this an, which is the sum when k is going from 1 to n minus 1 of sinus of 2k minus 1 pi over 2n over cosinus square k minus 1 pi over 2n cosinus square k pi over 2n. So the key is in this exercise is to split an as a telescope sum. So this is tricky. This part of the proof is tricky. How do you know in advance that you can split this as a telescope sum? So here you see that you have cosinus square at the bottom, right? So one thing that you should have in mind is this kind of splitting, right? So whenever you see this, you better think of a way of splitting a sum like this. All right. So this is the tricky part. you need to know this, and then you split it, and then because it is a telescope sum, you are fine. All right. All right. So next, I'm gonna and then once this is a telescope sum, this is the most difficult part of the proof. Once you know that this is telescope sum, then everything should be fine. All right. All right. So the next problem that I want to consider is the following problem, which is problem B4. So this is the 79th Putnam competition. Competition on 2018. So the problem is as follows. Given a real number A, we define a sequence by x0 to be 1, x1 and x2 are both A, and then you're going to have xn plus 1 is 2xn, xn minus 1, minus xn minus 2 for n bigger than or equal to 2. All right. So we have to prove that. Prove that if xn is equal to 0 for some n, then the sequence is periodic. Is periodic. All right. So this is again a very nice problem. So proof. So this is okay. Our topic is the series and limits, and this is a kind of limit that we have. So we want to see a limit which is periodic, right? So in this case, it's a periodic in the sense that the sequence is going to be repeating. So we have the first observation is that we first observe that A has to be bigger than 1, right? So the first thing we have to say that this is bigger than 1, right? So okay, so suppose that A is bigger than 1. All right, we will prove that xn plus 1 is bigger than or equal to xn for all n. Right. So if A is bigger than 1, then xn plus 1 is bigger than n. So in this case, you cannot have that xn is equal to 0, right? In this case, xn has to be bigger than x0, which is 1 for all n, and xn is equal to 0 cannot happen. All right. So first we observe that A has to be bigger than 1. Otherwise, xn plus 1 is bigger than xn for all n, and in this case, xn will be bigger than 1. And the case that xn is equal to 0 cannot be happen. All right. So to prove this, we're gonna prove by induction. we prove right. So first, for n is to be 0 and 1, we know that x 0 is 1, so it's bigger than 1. Right. So for n to be, for n is equal to 0, then you have xn plus 1 will be x1, which is a, and this is bigger than x0, all right, which is 1. So this is true. Now, when n is equal to 1, then xn plus 1 will be x2, and this is a, and this is also bigger than or equal to x1, which is a. So the claim is true for both n to is equal to 0 and 1. So now suppose that the claim is true for n to be equal to k. So in this case, you write xk plus 1 to be 2xk, xk minus 1 minus xk minus 2, all right? And this is bigger than 2 times xk, xk minus 1 minus xk minus 2. Right, by induction, we know that this is bigger than 2 times xk, xk minus 2 minus xk minus 2, all right? All right, so, and then this is bigger than 2xk, xk minus 2 minus xk, and then this is bigger than xk, 2xk minus 2 minus 1, so this is bigger than xk. Okay, so here we use the fact that you have xk minus 2 is bigger than xk minus 3, and it is bigger than x0, and this is equal to 1. All right. So thus by induction, we're going to have xn plus 1 is bigger than or equal to xn. All right. And this, again, this violates the assumption that we have from the beginning. We suppose that xn is equal to 0 for some n, and so in this case, this cannot happen. So basically, we can assume that, therefore, a has to be smaller than equal to 1. All right. Now, because a is smaller than 1, we can write and suppose that a is equal to cosinus of b, right? For b belongs to 0 pi. So now there's one tricky thing, which is the Fibonacci sequence. So let Fn be the Fibonacci sequence, which is defined as follows: F1 and F2 are both 1, and then Fn plus 1 is Fn plus Fn minus 1. All right. So we will show that Xn is equal to cosinus of Fn b. Right? So again, we want to prove this by induction. Right? So we will prove this by induction. By induction. All right. So we're going to prove this by induction. So this is true. This is true for n to be equal to 0, 1, 2. All right. So now suppose that this is true for n to be smaller than m, then 2xn xm minus 1 will be 2 cosinus of fm b and cosinus of fm minus 1b. And this will be, all right, by the standard formula for cosinus function, you're going to have this. All right. So, but you know that this is fm minus cosinus of fm minus 2b plus cosinus of fm plus 1b. All right. So which means that xm plus 1 have to be equal to 2xm minus 1 minus xm minus 2, and this is cosinus of fm plus 1b. All right, so this is a tricky part of the proof. So the thing here is that you have to think of a Fibonacci sequence and you associate that to xn. This is the tricky part of the proof. All right, and then there will be a so if you know this trick, you can construct similar problems. Say you can construct a sequence that is similar to Fibonacci, and then you integrate that into a sequence xm, and then the problem looks very difficult. All right. So now, as xn is equal to cosinus of f and b, so then so we go back to the original assumption, xn is equal to 0 for some n, right? Some n. So which means that f and b has to be, say, k over pi for some odd k. So which means that b have to be k over d of 2 pi, in which d here is for fn. All right, so you divide by 4, here you have 2, right? All right, so now let xn denote the pair fn plus 1. So each is fn plus 1 is viewed as an element of z over dz. All right. So since there are only finitely choices for xn, all right, so xn has to be, there must be n2 bigger than n1 such that xn2 is equal to xn1. All right. So which means that you have the sequence xn is periodic, meaning that xn has to be xn plus L for L to be equal to xn n2 minus n1. All right. So the most difficult thing in this problem is to realize that basically the sequence that you define from the beginning, this one, is associated to a Fibonacci sequence. So this is the key trick. All right. So from this trick, you can construct a new problem that may not rely on the Fibonacci sequence. You can put a number 2 or number 3 here. Doesn't matter. And then you can create similar problems. All right. So the key in this problem is the association of the sequence xn, so the Fibonacci sequence, by using cosinus sinus. All right. Thank you.